In this video, we are going to discuss the fundamental theorem of line integrals. So we'll state the theorem, and after that we'll look at an example of how you would apply this theorem in a specific situation. So let's begin by stating this theorem. Okay, so we're going to suppose this. Suppose that C is a smooth curve. Suppose that C is a smooth curve. Okay, so C is a smooth curve with parametrization. R of t, where t ranges between A and B. So suppose this is the case. We have a smooth curve C and it's parameterized by R of t, where t is between A and B. Okay. Also, suppose that f is a differentiable function. Okay. Suppose that f is a differentiable function let's say of 2 or 3 variables. So suppose that f is a differentiable function of 2 or 3 variables. All right. Okay. So we have a curve C. So far we have a curve C, which is smooth curve. It's got a parameterization R of t, and the parameter t ranges between A and B. And also we have f, which is the differentiable function of 2 or 3 variables. Okay. And let's also suppose this. Let's also suppose that the gradient of f. Okay. So let's also suppose that the gradient of f, denoted with a grad or nabla f, grad f or nabla f. So suppose that this gradient is continuous on C. Let's suppose that this gradient of f is continuous on C. Okay, so this is what we suppose for our theorem statement. We suppose that C is a smooth curve with a parameterization R of t, where t is between A and B, and we'll also suppose that f is a differentiable function of 2 or 3 variables. Let's suppose that the gradient grad f is continuous on this curve C. Okay. Now we say then the integral along C of the gradient of f dot dr is equal to the following. It's equal to f of R of B minus f of R of A. And that's basically what the theorem states. Okay, so let me say the theorem again. I'm going to say it again. Suppose that C is a smooth curve with parameterization R of t, where t is between A and B. Suppose that f is a differentiable function of 2 or 3 variables. Also suppose that the gradient grad f or nabla f is continuous on C. then the line integral, okay, the line integral along C of the gradient of f, which is written as we wrote it here, an integral along C of grad f dot dr, that's the line integral of the gradient of f along C. Then this line integral is equal to f of r of b minus f of r of a. Okay, so you basically evaluate r at b, and you evaluate r at a, and then you get this f of r of b minus f of r of a. So this is basically the theorem statement. Okay, this is the theorem statement for the fundamental theorem of line integrals. Okay, that's the theorem statement. So now we're not going to prove this. So we're not going to prove this theorem. We stated the theorem. We're not going to look at the proof. But as we said before, what we're going to do, we are going to look at an example of how to apply it. Just one example, just to show how you would apply this theorem for a specific situation. So let's go and do an example. Okay, let's go and do an example. So let's say example. All right. So now our example states the following. Okay, this is our example. Suppose that we have a gravitational field, and this gravitational field does work on a particle of mass m along some smooth curve or piecewise smooth curve, and we want to know what is the work that this gravitational field does moving this particle. Okay, so let's say what is the work done by the gravitational field? What is the work done by the gravitational field given by F is equal to minus m times big M multiplied by G over the norm of x to the power 3 multiplied by x. Okay, so what is the work done by the gravitational field given by this to move a particle of mass m? So to move a particle of mass m from point 3, 4, 12 to point 2, 2, 0 along a smooth curve, C. Okay, so that is basically what the example is saying. What is the work done by the gravitational field given by F is equal to this to move a particle of mass m from this spatial point to this spatial point along the smooth curve C. Okay, so now we have to solve this problem. Now to solve this problem, we do the following. Okay, let's just write solution. So now we're going to look at the solution of this problem. First of all, we note that the vector, this vector here, vector x, the vector x is given by this. So we note this. We note that x over here is basically the vector x y, z in space. That's what that is. So x denotes the vector x, y, z in space. Okay, now we also know that this field, this gravitational field that's given here, is a conservative field. This is a conservative field. All right. So that is another thing that we note, that F is conservative. F is a conservative vector field. So we say F is a conservative. F is a conservative vector field. F is a conservative vector field. So therefore, there obviously exists. There exists a function. There exists a function f such that f, the vector field f, is equal to the gradient of this f. Okay. So now, since we know this, we want to know exactly what is this function f. What is this function f such that the vector field f is equal to the gradient of this function f. For this particular vector field, we are given this function, and this function is the following. Okay, we're going to say where f, and it's of course a function of x, y, z. It's a function of x, y, z, and it's equal to m, small m, multiplied by big M, multiplied by g, divided by the square root of x squared plus y squared plus z squared. So this is basically now what we have. So now that we have all this information now, we can apply our theorem statement, okay, which is the fundamental theorem of line integrals statement. So we can apply now this statement to solve this problem. Okay, let's see. So we say therefore. We say the integral then along our smooth curve C of this vector field, which is of course the given gravitational field. The line integral of this given gravitational field along C is equal to the following. Since we know that F now is a conservative field, and this is the function F that we need for this problem. So what we can say is the following. We can say this is equal to the integral of the gradient of F along this curve C, okay, dot dr. All right, we know that it's conservative, that f is equal to grad f, so we can just write this down. So now that we've written it in this way, we can apply the theorem, because the function f is a differentiable function. Okay, this function here, function f, is a differentiable function, and also we have that the gradient of f is also continuous on this curve. It's a continuous function, so the gradient of f is a continuous function as well. So therefore, the conditions for the theorem are satisfied. The conditions for the theorem are satisfied. So we can go ahead and we can apply the theorem. So this basically means the following. So this means that this line integral, which of course describes the work done by this vector field. So this line integral here does describe the work done by this vector field, which is the given gravitational field. So this over here is equal to now f by, this is now by the theorem statement. This is equal to f of r of b, of course. But I guess at this point we can just go ahead and just write. We can just go to the second point that we're given. Remember, we're given 2 points. This vector field pushes the particle along this smooth curve C from point 3412 to point 220, and we don't have the parametrization for this this curve C, but we do have the actual spatial points, and we do have the function small letter f, that we need. So this is actually now equal to f of the second point, which is 2, 2, 0, minus f of the first point, which is the point 3, 4, 12. Is this. So now we have this function f, and of course this function f is given by this function over here. So now we go ahead and we just substitute into the function over there this value. So this is basically equal to the following. It's equal to small m multiplied by big M multiplied by big G over the square root of 2 squared plus 2 squared plus 0 squared. So we substitute this point in there and we go minus small letter m times by big letter M multiplied by G divided by the square root of 3 squared plus 4 squared plus 12 squared. We can factor out M multiplied by M G because it's common. So factor it out and then we are left with 1 over the square root of 2 squared plus 2 squared plus 0, we'll just leave out the 0, minus 1 over the square root of 3 squared plus 4 squared plus 12 squared. And M multiplied by big M multiplied by 13. So we can just write this. We can just leave it in brackets. If you work it out, you'll get 13 multiplied by the square root of 2 minus 4 divided by 52. So this will be our answer for this problem.